Good evening. Welcome to the last Center for Applied Math talk of the semester. This talk is always one of my favorite talks of the year because every year in the summer we run the Center for Applied Math. The CAM runs a summer research program, and at the end of the summer, students write up their work in these pretty professionally written reports. And based on these reports, we choose the winner of the Outstanding Summer Research Project Award. Is that what it's called, Pat? Anyway, the best research project of the summer. And the winner of this award gets to give one of the CAM talks, which I think is kind of a nice thing to do. I don't know. I hope. Anyway, and I really like this talk because it's really exciting to see what our students are doing as their summer research projects. They all do really, really outstanding work. And these two students did particularly outstanding work. So it is my pleasure to introduce fellow students, Laura Fink and Alex Bates, who won the award this past year. And they're going to talk to us about zero forcing number of circulant graphs. Thank you, guys.
Thank you, Dr. Stolarska. Thank you. So as Dr. Stolarska said, my name is Alex Bates. I'm a senior here at St. Thomas, getting ready to graduate. And after this semester, I will be moving on to pursue a PhD program in mathematics at the University of Iowa.
And I'm Laura Fink. I'm a junior here at the University of St. Thomas, and I'm an actuarial science major.
And as Dr. Stolarska said, we're here to talk to you about zero forcing number of circulant graphs. But before we dive into that, which sounds really, really technical, we're just going to go over what is a graph. A graph at its core is just a set of vertices and edges. We have an example here. The most intuitive way to think about it would be just a set of nodes that are connected via various edges. So in this case, the vertex 0 shares an edge with 1. 1 has an edge with 2 and 3, and then 0 as well, and then 2 has an edge, or shares an edge with 1 and 3.
So before we can get into the project, we have to talk about what is forcing, and to do that, we have to talk about the color change rule. So the rule is that if we have a graph that has a blue vertex, and that blue vertex has only one white vertex connected to it, then the white vertex is forced or color changed. So here, if we started with, say, vertex 0 being blue, it has only one white adjacent vertex. So that vertex is colored blue. And then from here, either vertex 1 or 2 can force vertex 3. So then a zero forcing set, we say, is the particular set of vertices that can force the entire graph. So in this case, when we started with vertices 0 and 2, we were able to force the whole graph. So that is a zero forcing set.
The zero forcing number then is the size of the minimal or smallest zero forcing set that will force the entire graph. So when we denote this z of g for a graph g, in our case here, it turns out that the zero forcing number is 2. That's the minimum number of vertices we need to start with that are blue to force the entire graph via the color change rule. The zero forcing set is not unique. In this case, 0 and 2 will force the entire graph, but so also will 2 and 3. 2 only has one white vertex that it's adjacent to, so that vertex 1 gets forced. Then vertex 1 only has one white vertex that's adjacent to, so then 1 forces 0.
So another interesting concept that we talked about a lot was propagation time. So if we start with a graph that has a certain number of blue vertices, we want to know how long does it take to color the entire graph. So here, if we started with 2 blue vertices at time 0, in one time step we can force 2 vertices, and then in the second time step we can force the next 2. So the propagation time of this graph would be 2. It's interesting to note the propagation time depends on the set. So if you have a different set, you might get a different propagation time.
So you might be asking yourself at this point, why study zero forcing number at all? What's the purpose? First of all, the first would be applications in the study of social networks. The best way to think about this would be, how does a trend propagate through a group? And where do you need to start with a certain number of vertices? To color the graph would be analogous to how do you start with a certain trend in a group to make the trend propagate through that entire group. The second, we found that a 2012 paper in the journal Discrete Applied Mathematics stated that a concept equivalent to zero forcing number has been used by physicists to study the control of quantum systems. So basically, physicists came up with an idea that was basically equivalent to zero forcing number, and we're using it to study quantum mechanics. Lastly, and probably what's driving the study of zero forcing in modern academia, in higher mathematics, is what's called the minimum rank problem, and zero forcing's relation to the minimum rank problem, which we will now describe.
So to talk about how circulant graphs relate to matrices, we need to talk about matrices. So a matrix is a rectangular array of numbers or symbols arranged in rows and columns. So let's say we had this matrix. It's a 3x3 matrix. What we're interested in is, what is the rank of this matrix? So the rank of a matrix, we say, is the number of non-zero rows in a fully reduced matrix. And the way we reduce a matrix is by row operations. So for example, we could take -1 times the first row and add it to the second row and get a new second row. So here we show just the operation, and now we have a simpler second row. And then if we add the second row to the third row and replace the third row, now we're down to only 2 non-zero rows. And we can continue to reduce this matrix fully. Go ahead. Adding the first and second row to get the new first row, and then multiplying the second row by -1. And now we can see in this fully reduced matrix, we have only 2 non-zero rows. So we would say that the rank of this matrix is 2. So now, how do matrices connect to the graphs that we were talking about? So on the graphs, the vertices and the edges represent a particular family of matrices that have a specific zero non-zero pattern. So if we had this graph, for example, each vertex is represented along the diagonal of the matrix, and everywhere where there's an asterisk there, that is a non-zero number, and that represents where we have an edge between 2 vertices. And then where we have zeros, that's where there's not an edge between 2 vertices. Now, when we say that a graph represents a family of matrices, what we mean is that we can have this same pattern, but have different matrices that fit the pattern. So for example, here are 2 different matrices in the same family. And go one more. We can see they have the same zero non-zero pattern, so they're both represented by that same graph.
So then the problem, or rather the minimum rank problem stated, is what is the minimum rank of all matrices in a given family that is to say with a specific zero non-zero pattern. And luckily for us, and the reason we're studying circulant graphs, or just graphs in particular, and their zero forcing number, is that the American Institute of Mathematics published a paper in 2008 stating that the zero forcing number of a graph was a bound for the minimum rank of its associated family of matrices. The equation that they gave is that the zero forcing number of a graph is always greater than or equal to n, that's the number of vertices within that graph, minus the minimum rank of the matrices associated with that graph. So in this case, what we're showing you is a graph and its specific zero non-zero, or the specific zero non-zero pattern associated with it. And we can compute on this graph what is the zero forcing number, and we find that it's 4. You need at least 4 vertices to starting blue, to color the entire graph. And knowing what we stated earlier, that the zero forcing number is greater than or equal to n times the minimum rank of the matrices associated with it, where this is a matrix associated with it, we plug in our values. So the zero forcing number is 4, greater than or equal to 6, which is the size of the graph and matrix, minus the minimum rank of that graph. And doing algebra, we see that the minimum rank of that graph is greater than or equal to 2. And we can plug in values for our graph there, given the zero non-zero pattern. And once this matrix has been reduced, we see that the rank of this graph is 2, and indeed for any graph that is size 7 or less, the minimum rank isn't, or the zero forcing number isn't just going to be greater than or equal to n minus the minimum rank, it's going to be equal. And in this case, we know that the minimum rank of any graphs of these type of what you saw earlier is 2.
That's, the minimum rank will be greater than or equal to 2, but it's saying with that pattern, we'll be able to find ones that are that particular minimum rank. Okay. So another important concept for these graphs is what is the degree? So the degree of a vertex is the number of edges that are touching the vertex. So here you can see vertex 0, the degree is 1. It has 1 edge. Vertex 1 is degree 3, and vertex 2 and vertex 3 are both degree 2. So the reason this is coming into play is let's talk about circulant graphs. This is where we did the majority of our research. So we say a circulant graph on n vertices with connections S and T. That's how you read the interesting notation. It denotes a graph with n vertices where every vertex has an edge between itself and the vertex that's S away from it and the vertices that are T away from it. So if you look at this graph and you look at vertex 0, this is the graph C1014. So it has 10 vertices. If you look at vertex 0, it has connections to each vertex that are 1 away from it. So that's 1 and 9. And then that are 4 away from it. So that's vertex 4 and vertex 6.
Circulant graphs are called regular graphs, and that means that every vertex within the graph has the same degree. So we talked about degree earlier. It's the number of edges that a given vertex shares with other vertices. And with circulants, every vertex has the same degree. So if you were to go through and count, you'd see that every vertex on this graph has 4 edges that are connected to it. And for a circulant graph, we saw that the degree is a minimum bound for the zero forcing number. So what do we mean by that? What we mean is that you need to start off with at least 4 vertices colored, or 4 vertices blue, to force even one vertex of the graph. So in this case, 0 has vertices 1, 6, and 4 adjacent to it. And since it is touching 9, which is white, 9 can become colored. Now, obviously, this isn't a zero forcing set for this graph, but it's just to show that to force even one vertex, we need at least 4 that are blue to start with. The study of circulant graphs also relies heavily on the use of modular arithmetic. For those of you who have had abstract algebra 1, 2, applied math 2, you'll know what modular arithmetic is right away. But the easiest and most intuitive way to think about this for people who haven't had abstract algebra is to think about it in terms of clock arithmetic. So let's say you wake up at 7 and you know that 7 hours away from 7 o'clock you have an event going on. Well, you add 7 to 7 and then that's 14 o'clock. But unless you're on military time, that doesn't make sense. We subtract 12 from it to then get 2 o'clock. So whenever we say mod, what we're doing is we're just subtracting multiples of whatever number is on the right-hand side of mod. And so in this case, 14 mod 12 is equal to 2, or 7 hours plus 7 a.m. is 2.
So the goal of our research project this last summer was to be able to state what the minimal zero forcing number was for every graph defined on n vertices with connections S and T, and to say what its propagation time was.
What aided a lot of our research effort was some code that I wrote at the beginning toward the beginning of our project in Octave, which is basically the same as MATLAB, if any of you have used that. And given an adjacency matrix, so the zero non-zero pattern we were talking about associated with any graph, our primary function computed the zero forcing number of the given graph by exhaustion. I say within machine capabilities because obviously you can't compute something that's 5 million by 5 million. It just won't work. However, one thing we did find is that a lot of the computations, especially for higher numbers, such as n equals 30, when the size of the graph is 30 vertices, the computations can take rather long, or a rather long amount of time. And we actually found that in certain cases, some of the computations took as much as a week and a half. So a rather long time. But we did find the zero forcing number of every circulant graph up through size 30. And the results that were generated from the code that we wrote gave us a great starting place from which to look at the data and then sort of extrapolate away from that and then make hypotheses and abstractions.
So one thing that we came across pretty early on was this concept of connected graphs. So we say that a circulant graph is connected if the greatest common divisor of n, s, and t equals 1. Otherwise, you have overlapping disconnected graphs. What we mean by that is, say we have this graph, 8, 2, 4. What we noticed is this is actually 2 copies of the graph 4, 1, 2. So if we were to look at the zero forcing number of 8, 2, 4, we would actually be looking at 2 times the zero forcing number of 4, 1, 2. So we had to take those ones out of what we were looking at.
Another idea that we ran into when we examined the code is we saw a lot of different graphs that had the same zero forcing number and propagation time, but it just didn't make sense why. And so we found that a lot of these graphs were what are called structurally equivalent. The technical term is isomorphic. The easiest way to think about this is if you have 2 graphs that you rearrange all the vertices, but the particular edges of those vertices are preserved, then the graph can be said to be structurally equivalent. And we found that a circulant graph on n vertices with connections s and t is isomorphic to every circulant graph on n vertices with connections a times s and a times t, where a is a constant that shares no common factors with n. And this was something that we proved in our research paper over the summer.
So just to bring up an example, if we were to have the circulant graph 814, it would be isomorphic to 8, 3 times 1, 3 times 4, or the circulant graph 8, 3, 12. But remember, we're doing modular arithmetic, so that's the same as the graph 8, 3, 4. So here we have the two graphs, 814 and 834. As you can see, each vertex is connected to the one directly across from it. So if we go ahead and look, you can see that they have that same connection. And then the other way that they're connected is just by a cycle that goes and touches each vertex once. So if we were to rearrange the vertices of 814, we would get exactly the graph 834. So we had to take out isomorphisms from our set of data or group them together because they have the same zero forcing number. So we only need to prove it once. So something else that we found was almost all of the graphs that are defined this way are degree 4. And it was sometimes useful to represent them with a different structure. So what we did is just kind of pulled apart in rings, I guess, the data. So this is the circulant graph 1214 represented as a circulant and then in this lattice structure. So you can see, for example, this is one ring of data here represented, and those two ends would be connected. So you can think of it kind of like a cylinder.
As we said previously, the degree of the vertices of a circulant graph is a minimum bound for the zero forcing number. Additionally, for a graph on n vertices with connections s and t, where s is less than t, the upper bound or maximum that the zero forcing number could be is 2t. And so we have a couple examples of this.
So just to give you an idea, this is saying, you know, whatever n, s, and t are, as long as s is less than t, we can say the zero forcing number is less than or equal to 2t. So, and the set would be, we have 2t vertices in a row, or right next to each other. So here, if we have the graph 12, 2, 3, our t would be 3, and 2t is 6. So the zero forcing number would be less than or equal to 6. So if we start with 6 in a row, we can see that vertices 2 and 3 only have 11 and 6 that are white, so they can force. And then the ones next to them can force, and so on until the whole graph is forced. So then the propagation time for any graph that uses this set, we would say is the number of white vertices that we start with divided by the number that force each time, and then rounded up because you can't have a partial time step.
That's what those weird looking brackets mean, because it means rounded up. Furthermore, we, and as a corollary, or what follows from the previous slide, is a circulant graph on n vertices with connections 1 and k. We found that the zero forcing number is less than or equal to 2k. And the minimal, or the set that is used to force is, again, just 2k vertices in a row. So in this example, for a graph on 17 vertices with connections 1 and 3, we just color blue vertices 0 through 5, which is 6 vertices, 2 times 3. And you can see that at each time step, we force up to a maximum of 4 vertices, 2 on each side. Thus, the propagation time is the number of white vertices that we start with, which is n minus 2k, divided by how many vertices get forced each time, which is 2k minus 2, and then, again, rounded up. And we conjectured, but we don't really know if it's true or not, that the set 0 through 2k minus 1, which is just 2k vertices in a row, is the minimal zero forcing set for every graph of this type for n greater than or greater than k squared. So this is open. If anybody else wants to do research on this in the future, this is one particular direction to take it.
So the reason we said when n is greater than k squared is because there is a special case when n equals k squared. If we have the graph k squared 1k, we know that the zero forcing number is less than or equal to 2k minus 1. This was actually proven in research that was done in 2010 by another St. Thomas student, Lin Duong. And the way she set up the proof was, if we have k squared 1k, so here 3616, this actually gives us 6 hexagons that are all connected to each other. And if we start with 2 full hexagons, that's 2k vertices, and if we take out 1, we can still use that set to force the entire graph. So here, this is 2 hexagons, and then minus 1, and then we can see that they force outwards in kind of a strange pattern and force the entire graph. What we added to this proof was we wanted to prove what the propagation time was. So this was where it was really useful to lay it out in a lattice structure. So this is the same graph, represented differently. And if we start with 2 full rings, minus 1 vertex, we can see that we force to the top and the bottom first, and then force towards the middle until we have 2 full columns that are colored, and then we force outwards. And this representation allowed us to write a proof for the propagation time, which does turn out to be k minus 1. So in this case, 5.
Another pattern that we noticed is that for a circulant graph on n vertices with connections 1 and n over 2, where n is even, we found that the zero forcing number is 4. And that you can read the set there. That'll become more apparent through this example. So in the case of the circulant graph on 12 vertices with connections 1 and 6, we find that the degree of each vertex is 3. So each vertex on that graph has at most 3 edges that it shares with other vertices. And so since the degree is 3, that's the minimum bound for the zero forcing number, we found that we just needed 1 more vertex to color the entire graph. So starting with 4 blue vertices, 2 adjacent, and then across from each other, we find that it forces around the graph at each time step. And we see that the propagation time is the number, again, of white vertices that you start with over the number of vertices that are forced at each time step, rounded up. And in this case, we also looked at the case where you have a circulant graph on n vertices with connections 1 and the floor, or rather n divided by k rounded down, where n is odd. We found that the zero forcing number is less than or equal to 2k, and moreover that it's a special case of isomorphism, so the structural equivalence that we were talking about earlier. We found that this graph is isomorphic to the circulant graph on n vertices with connections 1 and k, where n is equal to 1 mod k. And furthermore, if n is odd, then the circulant graph on n vertices with connections 1 and n over 2 rounded down for odd n is isomorphic to the circulant graph on n vertices with connections 1 and 2. It's pretty much the most basic graph you can get. So we have an example of this, and we're just going to show the isomorphism here. In this case, if we start with 1 vertex that's blue and just walk around on circulant graph on n vertices. On the right, that should read circulant graph on 9 vertices with connections 1 and 2, and this is 9, 1, 4. We can just walk through a cycle to show that they're structurally equivalent. Similarly, if we walk around the outside of n14, there's another cycle within n12. And that's just showing that they're structurally equivalent.
So we have a couple further research questions that we were thinking about as we wrapped up our project last summer. And so one of them was, are there properties of circulant matrices that can give us further insight into zero forcing number of circulant graphs beyond what we already know? So if we did more research or...
Yeah, if we did more research into the properties of circulant matrices, would that give us any more information about circulant graphs? On the other hand, if we did more research on circulant graphs, would that give us more insight into circulant matrices? Because there seems to be, there is a connection between the two, but we're wondering, is there more than what was already proven with the minimum rank problem?
We also wanted to know if the things that we discovered about our circulant graphs, if they can be applied to directed graphs. So the graphs we were looking at are undirected because when you have an edge between two vertices, it goes both ways. But there's also been study on graphs where the connection only goes one way. So we want to know if the stuff we looked at applies to those types of graphs.
This question was posed by Dr. Rodden in the math department. Given a graph G, is it possible to find zero forcing sets for that graph that will give us a range of propagation times? We know that the smallest the propagation time could be is 1. That's if we just had every vertex blue and left one white. And we know that also it could be, at the very least, as great as the propagation time associated with a given zero forcing set. So we're just really wondering, can you generate a range of propagation times for a given graph just based on what you know about the graph?
We also wanted to know if we're given a particular graph, can the zero forcing number be expressed in terms of just the constants n, s, and t without any further computation? So this is kind of the idea of, is there an overarching rule or set of rules where we could just look at the relationship between these numbers and immediately know what the zero forcing number is? So I think we've contributed to that a little bit, but I think there's still a lot that could be done.
Finally, some thank yous are in order. We want to thank our advisor, Dr. Kroschel, who was really just instrumental in our research and just helped us get off the ground. And we also want to thank the Center for Applied Mathematics that hosted the CAM Summer Research, and without whom none of this would have been possible. Similarly, thank you to Drs. Van Fleet and Stolarska, as well as Ms. Christine Henriksen, who also helped make all this possible and for putting in all their hard work. And lastly, we want to thank the entire math department, all of our professors that have taught us, given us guidance over the years. And I can truly say on both Laura's and my behalf that we're grateful for you, for all the hard work that you put in for us, and we're grateful just for all that you've taught us over the years, and we can say too that we would not be here without you all. So lastly we have the most exciting part, our references, and that's it. Are there any questions that people had?
First of all, thank you guys. Questions for our speakers?
Yeah, I think we can upload them, can't we?
We might be able to. Worst case, you can give them to me, and you can send me an email that I can just forward to you. We've never uploaded slides before, so I can look into that. And in fact, you're the second person that's asked in the last 2 weeks, so maybe we should.
As long as there's no copyright problem, every student has their own personal webpage posted by St. Thomas.
Right, right. But I'm thinking about putting them on the campus. Other questions?
You said earlier that you wrote this, the code for most of this in MATLAB, and it's a little bit bulky and brute force. Have you ever thought of rewriting it?
Yeah, we had thought of rewriting the code in Fortran or C, just because, and that sounds archaic, but really we needed things that could compute quickly and do tons of computations a second. So that was considered, but unfortunately we didn't have enough time in our summer research to actually implement that.
I have a question, Alex. At each point when vertices were forced to change their color, it looks like the same number always changed. Is that completely obvious why that's true?
I can take this one. So I think that that's just true of circulant graphs because they're regular graphs. It just so happens that if the vertices are arranged the same way and have the same connections, then a set that causes things to force will usually cause them to force symmetrically. So true, not in the k-squared case. That was kind of a strange one.
Yeah, absolutely.
Might take a while.
Go grab some cookies if you want. All right, there we go.
Go back to
The lattice? Okay.
forces one last each.
Mm-hmm.
The one direction force 3 or force 5.
Two at that time step, 3 at that time step,
You
and
don't see that if you don't put
8.
it in the lattice.
Yep.
In that same graph, why did 5 go over
Because 5 is also connected to 35, because they connect around as well. So 5 is connected to 35 that's white, so it can't force down because it has 2 that are connected that are white.
I have a question. Could you guys just tell these students if you feel like doing summer research, like for example, Alex helped you get into grad school, or if you've gotten any feedback along those lines, or I don't know if you've applied for any internships at this point, but even though this is not an actuarial science project in any sense, did it make any difference when you were applying for internships or grad school programs?
I would say it definitely looks good on a resume. It's something that's, if you really get to know your subject, it's something that you can talk about confidently with interviewers. So that was something I really enjoyed. It also just fostered my love of mathematics. So it's a great way to, I guess, explore mathematics, and it's also a unique opportunity. You don't always get the chance to do research. So if you can do that while you're in college, it might be a good thing to try.
For me personally, I didn't know what to expect coming out of summer research, but I remember A, putting it on my resume, and then B, writing about it in every cover letter that I sent to all the grad programs that I applied to. And I don't know, I never got any feedback on how effective that was. But I mean, I got into grad school, and I would say, I think just for me as somebody who's going to be doing mathematics for foreseeably the rest of his life in some capacity, I think that summer research really furthered, it sharpened me as a thinker, as a mathematician. I learned how to write proofs probably better than I knew in the past. Before it was just all of my proofs were very symbolic and didn't have a lot of English, and I didn't communicate myself very well. Dr. Kroschel is smiling because she knows. But I learned how to write proofs well in really, really good, well, not really good, but I'm an undergrad, but decent English for my grade. And I would say it's probably been one of my most formative experiences in the math department in my undergrad to this date. And I would recommend it for at least one summer.
Yeah, one more question?
How did you find this project?
That would be thanks to Dr. Kroschel. This is her project, so she kind of gave us the basics and said, here, go play with the numbers. So that's how we started.
I can tell you that each year, and in fact, maybe I'll use the microphone so it's recorded. Each year we have a summer research program, and the way that that program works is usually students either talk to their professors if they're interested in doing research. So suppose you're in a certain class with a certain professor, you know, you may want to just talk to them to see if they're doing any research projects. Otherwise, students come and talk to me, and I'm the associate director of the CAM, so I have some idea of what types of projects different faculty are working on, and I try to pair students up with faculty. But generally, these research projects come from the research interests of the faculty in our department. And of course, I think in the past, you know, we've kind of geared them towards the interests of our students to some degree. But that's if you're interested in doing a summer research project, you should certainly come and talk to me. If not this year, then sometime in the next year or so. Anybody else? All right, thank you guys again for